In the previous class, we saw characteristics of practical selective filters and we saw symmetric and asymmetric FIR filter. In that, we went on with respect to case 1 where we considered the value of m as even and the condition be symmetric. Now, let us move on to the second case, that is let m be odd and symmetric. So, if I write the Fourier transform equation of unit sample response, h of omega will be equal to summation n ranges from 0 to m minus 1 h of n into e power minus j omega n. Now, what I have done is I have considered the value of m as odd. So, let us take a value for m. Let m be equal to 9. So, if it is equal to 9, the sample starts from 0, 1, 2, 3, 4, 5, 6, 7 and 8. Okay. So, again I need to divide this summation and I need to continue the derivation in order to find out what is the magnitude plot as well as what is the phase plot. For that, here I have odd numbers. So, let us divide the first group with 4 samples and the next group let it have only 1 sample and the last group be having 4 samples. If so, the lower limit of first summation will be 0 because the indexing itself is 0. So, what should be the upper limit? So, the upper limit should be 3. If I want it to be 3, what I can do? I can subtract 3 from m, that is the value of m is 9. So, if I subtract 3 from 9, 9 minus 3 gives us 6. So, from 6 I can obtain 3 by dividing 6 by 2. So, 6 by 2 gives us 3. So, what will be the upper limit? It will be m minus 3 by 2. M is 9, 9 minus 3 is 6, 6 by 2 is 3. Similarly, I need to check what is the value for this. Okay. So, I need to get the indexing as 4, but the value of m is 9. So, 9 minus 1 is nothing but 8. So, 8 by 2 gives us 4. So, I can write the standard limit as m minus 1 by 2. M is 9, 9 minus 1 is 8, 8 by 2 is 4. Similarly, I need to check for the condition where I need to get the indexing as 5. So, in order to make it as 5, so I can add plus 1 to m. If I add plus 1 to m, 9 plus 1 is 10. So, if I divide 10 by 2, I get it as 5. So, the lower limit of second summation is m plus 1 by 2. M is 9, 9 plus 1 is 10, 10 by 2 is 5. So, finally, the upper limit will be m minus 1. So, 9 minus 1 is 8. So, this is the important thing which we need to remember whenever we divide the summation, how we set the lower and upper limit. So, if I divide this particular summation into 3 parts and if I rewrite, therefore, h of omega will be equal to the first summation and its lower limit is 0 and the upper limit should be m minus 3 whole divided by 2 into h of n into e power minus j omega n, okay, plus in the second group I have only one term. Since I have only one term, there is no need to write the summation. We use summation whenever we are taking the sum of more than one number. Here we have only one sample, so I will write it as it is, that is instead of n, the value of n should be m minus 1 by 2. So, these are nothing but the limits for small n. So, n should be equal to minus m minus 1 by 2. So, wherever I have n, I will replace it with m minus 1 by 2. Since I have only one term, I will not write summation for the second term, that is h instead of m, I will replace it with m minus 1 by 2 into e power minus j omega. Instead of 8, I need to replace it with m minus 1 by 2 plus. We are done with these two things. Now, I need to write the summation for the next group. So, the lower limit is m plus 1 by 2. So, I will write it here, the third term n ranges from, what is the lower limit? It is m plus 1 by 2 and the upper limit is m minus 1 into h of n into e power minus j omega n. Hope it is clear how I divided the summation into this equation. Okay. Now what let us do is, as we did in the previous case, let us take substitution for the second summation. Let us take the new value for n and let us simplify the summation part so that it will be easy for the purpose of simplification. So, let the new value of n be equal to m minus 1 minus n. Okay. If so, if the value of n is equal to m plus n by 2, m plus 1 by 2. If the value of n is m plus 1 by 2, what will be the new value? Let me check. That is n new will be equal to m minus 1 minus m plus 1 by 2. Okay. So, if I simplify this, I can take LCM. So, if we take LCM, so it will be 2m minus 2 minus m minus 1. So, if I simplify this, what will be the new value? 2m minus m is m minus 2 minus 1 is minus 3 divided by 2. So, the new limit which we got is m minus 3 by 2. Similarly, if the value of n is equal to m minus 1, if n is equal to m minus 1, then the new value of n will be equal to m minus 1 minus m plus 1. Again, these two gets cancelled and these two gets cancelled, therefore the value will be equal to 0. Now, in the next step, in this particular term, what let us do? Let us take the new substitution, that is n new, in second summation. If I do so, the limits also changes as we saw. So, let us put all these things in the second summation and let us rewrite the equation for h of omega. So, h of omega will be equal to summation n ranges from 0 to m minus 3 by 2 h of n into e power minus j omega n plus h of m minus 1 by 2 into e power minus j omega m minus 1 by 2 plus, so I need to rewrite the value of n as m minus 1 minus n and I need to change the limits. So, that will be equal to summation n ranges from m minus 3 by 2 to 0 h of m minus 1 minus n into e power minus j omega m minus 1 minus n. Now, what let us do? Since the condition which we are taking is symmetry, we know that for symmetry, for symmetric, h of n will be equal to h of m minus 1 minus n. So, this is the condition. So, in the next step, let us change the order of summation and instead of h of m minus 1 minus n, let us substitute it as h of n. So, if I rewrite the equation, therefore, h of omega will be equal to summation n ranges from 0 to m minus 3 by 2 into h of n into e power minus j omega n plus h of n minus 1 by 2 into e power minus j omega into m minus 1 by 2 plus summation n ranges from 0 to m minus 3 by 2. So, instead of this, I will replace it with h of n from the symmetric condition. into e power minus j omega m minus 1 minus n. So in next step what let us do is, I will rewrite this exponential term separately for m minus 1 as well as n. If I do so, what will be the equation for h of omega? H of omega will be equal to n0 to m minus 3 by 2 into h of n into e power minus j omega n plus h of n minus 1 by 2 into e power minus j omega m minus 1 by 2 plus summation n ranges from 0 to m minus 3 by 2 into h of n into e power minus j omega m minus 1 into e power minus into minus gives us plus j omega n. Now what I can do is, looking into this summation as well as this summation, I can take summation n ranges from 0 to m minus 3 by 2 into h of n as a common factor. Yes. So for that what I will do is, I will write this term as the first term. So let us not disturb that. Then let us take common factor. Therefore h of omega will be equal to h of n minus 1 by 2 into e power minus j omega m minus 1 by 2 plus summation n ranges from 0 to m minus 3 by 2 into h of n into e power minus j omega n plus e power minus j omega m minus 1 into e power j omega n. Now what let us do is, so I will assume this is multiplied with 1. So instead of 1, let us incorporate a exponential term that gives us e power minus j omega m minus 1 by 2. So if I do so, the equation h of omega will be equal to h of n minus 1 by 2 into e power minus j omega m minus 1 by 2 plus summation n ranges from 0 to m minus 3 by 2 into h of n into e power minus j omega n. I am rewriting it as it is, into, instead of 1 I can write it as e power minus j omega m minus 1 by 2 into e power plus j omega m minus 1 by 2. So if I combine these two exponential term, I will get it as e power 0. We know e power 0 is nothing but equal to 1. Similarly, here I will divide this exponential term in terms of m minus 1 by 2. So if I rewrite the term e power minus j omega m minus 1 by 2 into e power minus j omega m minus 1 by 2 into the last exponential term is e power j plus j omega n. Now looking into the exponential terms that are inside the bracket, I can take this term and this term as a common factor. Yes, so let me take those two terms as a common factor. Therefore h of omega will be equal to h of n minus 1 by 2 into e power minus j omega m minus 1 by 2 plus summation n ranges from 0 to m minus 3 by 2 into h of n into e power minus j omega m minus 1 by 2 into, so what are the terms left out in the first term? E power minus j omega n into e power plus j omega m minus 1 by 2 plus e power minus j omega m minus 1 by 2 into e power plus j omega n. So in the next step what let us do is, let us combine these two exponential term and rewrite. Let us combine these two exponential term and rewrite. So if I rewrite this equation, that is h of omega, so I can write it as h of omega, which is equal to h of n minus 1 by 2 into e power minus j omega. So this has to be n, I have written it as m. So we have taken the variable as m. So this should be m. So in the previous step also, wherever I have written it as h of n minus 1, it should be h of m minus 1. So kindly look into that. So this will be h of m minus 1 by 2 into e power minus j omega m minus 1 by 2 plus summation n ranges from 0 to m minus 3 by 2 into h of n e power minus j omega m minus 1 by 2 into e power. So in these two terms I will take e power j omega as common factor. So m minus 1 by 2 will be left out in this term, and here it will be minus n plus e power. Again here I will take minus j omega as a common factor. Minus j omega m minus 1 by 2 minus n. So this is the equation which we are going to get after taking the common factors of exponential terms. Now looking into this equation, especially this term, is it in the form of e power j theta plus e power minus j theta? Yes. So what we know? Let me write it here only. That is, we know that e power j theta plus e power minus j theta is equal to 2 cos theta. Yes or no? According to this particular exponential term, what is theta? Where theta is nothing but equal to omega into m minus 1 by 2 minus n. Okay. In the next step, instead of e power minus j theta plus e power plus j theta, let us write it in the form of cosine. So if I rewrite the equation for h of omega will be equal to h of m minus 1 by 2 into e power minus j omega into m minus 1 by 2 plus summation n ranges from 0 to m minus 3 by 2 into h of n into e power minus j omega m minus 1 by 2 into 2 cos omega m minus 1 by 2 minus n. Okay. Now in the next step, what I can do is I can rewrite this 2 outside the summation. Similarly, in these two terms I can take e power minus j omega m minus 1 by 2 as a common factor. Yes. Therefore, h of omega is equal to h of m minus 1 by 2 plus 2 into summation n ranges from 0 to m minus 3 by 2 h of n cos omega m minus 1 by 2 minus n into e power minus j omega m minus 1 by 2. So now this is in the standard polar form. So this is the magnitude term and this is our phase term. So if I rewrite, magnitude of h of omega is equal to h of m minus 1 by 2 plus 2 summation n ranges from 0 to m minus 3 by 2 into h of n into cos omega m minus 1 by 2 minus n. Okay. So this is with respect to magnitude. So if I write with respect to phase, I can write it as, so and phase of h of omega will be equal to, so what is the phase? It is nothing but minus omega m minus 1 by 2. That is it will be equal to minus omega m minus 1 by 2. It will be equal to minus omega m minus 1 by 2 plus pi. Now, looking into this phase condition, so this term, that is m minus 1 by 2 and m minus 1 by 2, for both the cases when magnitude of h of omega is lesser than 0 or when magnitude of h of omega is greater than 0, it is a constant term m minus 1 by 2. So, m is nothing but the value which we take, whether it is even or odd. Since that is a constant value, so we can conclude that the phase of an FIR filter varies linearly with respect to omega. So, this is with respect to case 2, where the value of m is odd and the condition which we take is symmetric. So, in case 3 and case 4, we need to check for m value even and odd, and the condition should be antisymmetric. If we move on to the antisymmetric condition where m is even and odd, so this will be the magnitude when we consider the case antisymmetry and the value of m is even. So, magnitude of h of omega will be equal to 2 into summation n ranges from 0 to m by 2 minus 1 h of n into sin omega m minus 1 by 2 minus n. Similarly, for the antisymmetric condition only, if m is odd, the magnitude of h of omega will be equal to h of m minus 1 by 2 plus 2 into summation n ranges from 0 to m minus 3 by 2 h of n sin omega m minus 1 by 2 minus n. So, if I look into the phase condition, so for both even and odd, the phase conditions are same, that is angle h of omega will be equal to pi by 2 minus omega m minus 1 by 2 when magnitude of h of omega is greater than 0, and for it lesser than 0, it will be equal to 3 pi by 2 minus omega m minus 1 by 2. So, this is the phase condition. Again, looking here, the term m minus 1 by 2 is a constant term. Therefore, we can conclude the phase varies with respect to omega. Therefore, FIR filters are linear phase filter. So, this were the concepts related to symmetric and antisymmetric filters, FIR filters, where we dealt with 4 different cases. So, we derived case 1 and case 2. So, I want you people to try it for case 3 and case 4 by taking the value of m as even and antisymmetry and the value of m as odd and antisymmetry. When you try to derive, these are the magnitude quantities and this is the phase quantity which we are going to get. This completes the concepts related to symmetry and antisymmetry FIR filter. In next class, let us see how to design an FIR filter using various windowing techniques, and then we will move on to the realization of FIR filter. Thank you for today's session.